types of inverse problems. As I said, when you're trying to determine, whether it's cancerous, whether you have cancer cells or whatever, you have to decide on the physics, right? What is it that this problem is, which physics is best suited for this problem? And once you've made that decision, and then you use that method of trying to determine. So, the physics might lead you to an elliptic problem, a transport equation, a hyperbolic problem, or something else, right? So my idea was to show you three different inverse problems arising from three different types of physics. So I first showed you the elliptic case, and then I started on the transport equation, and I was somewhat through there, but I still wanted to show you some more results there, including I didn't give you any open problems there, and there are a few. And then once I'm done with that, today I will start giving you an example of a hyperbolic inverse problem. Okay, so let me remind you of the problem for the transport equation. Just right. So what we have is that you have, I don't know if it's really done or not. You have some tissue organ, and maybe there are or may not be cancerous cells, and you send in particles, and the particles have a specific velocity, right? Speed is one. The velocity is really giving you the direction of the particle, and then it goes, interacts in the medium. It's either absorbed and scattered, correct? Right. It's absorbed and scattered, and then it comes out, and you're measuring what's coming out, and from that, you want to determine the absorption coefficient at each point and the scattering coefficient at each point. And once you know those things, that will tell you, okay, maybe cancerous cells have high absorption or high scattering, and non-cancerous cells have, low. So that will tell you, whether it's cancer or whatever you're trying to look for. Okay, so just to remind you again, S is the unit sphere in RD, and it will represent the directions, the direction in which the particles will travel, the velocities. Remember, speed is always one. Okay, D is the bulb, it was convex. This is very important in some of the things I did. I think you have Professor Varinathan had asked me about convex or non-convex. Whatever I'm doing, at least one of the things I did depended very much on it being convex. The results may be true for non-convex though. Okay, so what is it that is sort of being measured? It's the density of particles with velocity v. You choose a direction v. What is the density of the particles with velocity v at x at time t? So that is the function which is going to satisfy the transport equation. And this is the absorption coefficient at each point. It's a non-negative number. The absorption depends on the velocity, meaning if a particle comes with certain velocity v, the amount of it which is absorbed depends on that direction and the point also, of course. Then the scattering coefficient, k, depends on the incoming direction and the direction in which it produces the particle is scattered. And then the physics, this is the physics. The rate at which the concentration of particles traveling with velocity v at position x at time t depends on, this is just due to the transport. The particles are moving, so that's why they're coming and leaving. So this is the contribution from that. This is the contribution from the absorption. That's why the negative sign, right? The particle arriving at velocity v at position x time t, this fraction of it is absorbed. And if it arrives at velocity v prime at time t at position x, then it produces a particle with so many particles with velocity v. And you do this for all incoming directions, and that's why you add it up. Okay, so this is the physics. And what was the inverse problem? The inverse problem was, so you're going to prescribe incoming densities. Now you cannot prescribe densities. So if you cannot say, what is the concentration of the particles with velocity v at this point, because things are leaving there. You cannot control that. You can only control things where there are incoming directions associated to the point. So that's why we define this incoming and outgoing. I call them boundary velocity pairs. So if x is a boundary point, then v is an incoming velocity if the dot product of the velocity with the outward normal is negative. So those are the incoming directions at the boundary point x, and these are the outgoing directions. And if you're going to prescribe concentrations, it's only going to be at the incoming direction. You cannot prescribe them here. Okay, here you can only measure. So that's what I did. So I defined this was just a notation. So this is the forward problem. So you prescribe the concentration on the incoming part, and there's no concentration initially, and that's a well-posed problem. So you define the albedo operator, you prescribe the incoming concentration on the incoming boundary, and you measure the concentration in the outgoing part. And the question is, if you do this experiment, which means if you know the operator, which means you know the response to every possible input, can you determine the absorption coefficient sigma, which depends on position and velocity, and the concentration, the scattering? Okay, right? Remember, your measurements are only on the boundary. You're trying to get information about the interior. Okay, that's what makes these problems hard. Okay, so some people ask me this question, and I want to answer that, but to remind you of something. So we always try to figure out, is it an overdetermined problem, underdetermined? So the albedo operator, corresponds to knowing this so-called Schwartz kernel, and we did this calculation. This depends on 4D minus 3. D is the number of dimensions you're working in. And then whereas what you're trying to recover, this depends on 2D minus 1 and this 3D minus 2. So for dimension D greater than or equal to 2, this is always greater than this and post. So all the problems are overdetermined, meaning we have more information than supposedly we should need. Okay? And this is important for one of the, so to answer one of the questions that someone asked me yesterday. Okay? So,
problem of getting both or problem of getting only one?
Both. See, okay, now this is something else that someone asked me. So he asked me, so this is 4D minus 3, and you're trying to recover this. So the number of unknowns should be 3D minus 2 plus 2D minus 1. Right? But that's not the right way to look at it. Okay? Sorry. So why am I saying that? Okay? Suppose let's say this thing depends on, how many variables, if you have two functions, how many variables does it depend on? Let's say I have two functions on the real line, right? Should I consider them as a function of, two functions as a function of two variables or a function of one variable? Okay, I argue that you should really count them as function of one variable. Okay, here is this, right? So if you have one function on the real line, I can shrink it and map it into half a line. And take the other function and map it into the other half. So the two functions can be thought of as really one big function on a line. So if you think like that, really, so having two different things, it's really you go and count the larger thing. That's the way I look at it. Is it working? No. Hello? Is that is that better? Is that okay?
When you speak loud, it's okay.
Hello? Yeah? Hello? No? Hello? Yeah, is that better? Yeah, that's good. Okay. Thank you. So that was, something's happening. When I'm turning this.
Position it differently.
I think if it below, it may help.
Better? Okay. Hello? Yeah. Is that okay?
Yes.
Yeah. Okay. So this is one of the questions someone had asked me yesterday, and this is all heuristic, right? This is not a theorem or anything. So it's just a way of thinking. So in my opinion, I think, so when you have to compute two functions and you compare it, you just pick the bigger one and think of that. That's my heuristic. Okay? And I've tried to explain why I think like that. Okay? So that was one question. So remember that this is an overdetermined problem. And then someone else asked me, I think it's Professor Manina. So, we are solving this problem, and Right. So other thing I said was that when you're prescribing the concentrations on the incoming part, you can replace that by is that working? Yeah. You can replace that by an initial value problem, right? Let's do that. Okay. And then what I said was to solve the problem, you put a source outside. I think it's skipping off and on, right? Right. So what I said was you place the source outside the domain in a certain direction. Yeah. I don't know what's happening. Okay. Yeah? Okay. So you put your I think it's going away. Okay. Yeah. All right. So, fine again.
So, Fazal, did you change the battery?
Okay. All right. So you can hear coming and going. The other thing is this thing is loose. You turn this off. The older broke also. You know how no? Okay, well, I just hold it in my hand. That's fine. I see. Okay, let's try. Okay, so the way we were going to do the problem was we'll put a source outside and put a particular direction and let things go. And so what I said was that if you write the solution, then you get the most singular part, then the slightly less singular part, and then U2, right? And then what I said was that, yeah. So I said you just look at the information coming from when you measure U on the boundary, you can extract from it the pieces U0 and U1 pieces also. And I said you can do the reconstruction based on just what you extract from U0 and U1. So Professor Vaninathan, I think, or someone else asked me, he said, well, you seem to be able to get your answer without using U2, right? And how is that? And then this is where you come in. You notice that the problem is overdetermined. So you don't need to use all the information. That's why you're able to, that's why you're able to solve the problem just by extracting the information from U0 and U1. So that's the answer to the second question, right? Because the problem is overdetermined. If a problem is formally determined, you're not going to get that lucky, right? You will not be able to escape without using U2. In fact, U0 and U1 will almost give you no information if it's a formally determined problem. Okay? It's because it was overdetermined that you were able to just get everything you wanted from that. Okay, so these are the two things I wanted to tell you. Okay.
So, are there partial data results in this?
So I'm going to come to that next. Okay. So what I want to do next is I want to go to the stationary problem, okay, where you don't have information. You're looking at the state of the transport equation when things have settled down to a steady state, okay, that the concentration is not changing with time. And let's look at those problems. So when the concentration is not changing with time, then U sub t is 0, then the left part of the equation goes away, and you're left with just the transport part, the travel part, the absorption, the scattering, and because it's not steady state, it's equal to 0. All right. Now, so there is no time involved here, and this is happening. Maybe I just stop this. Can you hear me without it?
Yes, you can.
Okay. All right. So if you don't hear me, just tell me to speak louder. All right. So this is happening in the domain D and the directions velocity V. And what you do again is you prescribe the concentrations on the incoming part. But there is no time involved. Right? So now you define the time-independent albedo operator. Okay? So you prescribe the incoming concentration F, which is time-independent, and you measure the outgoing part. By the way, this problem is not well posed in general. You need to impose a little bit of condition because, you know, to reach a steady state, you have particles coming in, particles leaving. They may not reach a steady state. So you need to impose a few conditions on sigma and k so that it reaches a steady state. Okay? And the conditions are not very strong. I mean, something about the norms or something and so on. Okay? So if you read the review paper, the conditions are given there, which guarantee that this will have a solution. Okay? So I'm not focusing on that aspect. Let's assume that. So you define the albedo operator, and then the same question is, can you recover the absorption coefficient and the scattering coefficient? Okay? So I'm giving you now one parameter less information. There's no time involved in it. So you have a little less information, you're still trying to get the same thing. So it's an even harder problem. So in fact, if you do the parameter count, well, I didn't even bother doing it, but it's one less than what you had before for the data. But basically, whatever we did for the time domain, in fact, in the same paper, they proved this thing itself, and it's really a continuation of the time domain. They use the same argument. So they say that if the albedo operators are the same for two of them, sigma 1, sigma 2, k1, k2, and if, as before, the sigma 1, sigma 2 are independent of velocity, then there is uniqueness. Now, that is only true for all dimensions 2, greater than or equal to 2, but they do not say anything about k1 and k2. But for dimensions greater than or equal to 3, the k1 will also equal k2. Whereas in the time domain case, d greater than or equal to 2 was enough. But remember, you lost one piece of information, the time information, so that's why the dimension goes up. Okay? So that is the result in the time independent, the steady state case. Okay. So notice that I had to assume that sigma 1 and sigma 2 were independent of velocity. Are there any results in which you can actually recover the absorption coefficient which depend on the direction? Right? Are there any results? And at first glance, it seems that there are no results. Okay? Because there is a non-uniqueness example. And this was constructed again in the paper by Stefanov and Chilby. They said, pick any function phi of x and be a positive function on the domain and all directions. Any positive function, doesn't matter what. And of course, you want it to be 1 on the boundary and s. Okay? And they say that you give me any sigma and k. I'll construct for you another sigma and k, which I'll call sigma prime k prime, which have the same albedo operator. And the construction is, I'll give it to you. You just have to, you can sit down and do it yourself, you can verify that it works. Here's the construction. Sigma prime is, take the original sigma and subtract from it the gradient of phi divided by phi. Remember, that's why I need phi positive. Times the dot velocity vector. So there's a new absorption coefficient, and the new scattering coefficient is, take the old one, multiplied by phi xv over phi xv. And the corresponding concentrations are, basically take the old one, multiplied by phi. And so if U corresponds to the sigma and k, then U prime will correspond to sigma prime and k prime. You can verify. Just check it, just plug it in, you check it, go through the calculations, it comes out. Okay? Now you prescribed F, the concentration for U, but phi is 1 on the boundary. So even this same, keeping the same boundary condition, you even satisfy the boundary condition. And also, what about the normal derivative? Well, you will not, well, not normal derivative. U prime on the outgoing part will also agree with the U. So basically, the two albedo operators are the same. Assuming that this result is true. I mean, like, it does satisfy. You can check it yourself. It's nothing, not a difficult computation. So it says that, well, if you're trying to recover absorption coefficients and scattering coefficient which depend on velocity, you're out of luck. At least at first glance, it seems so. Except one thing, which is what saves you, right? Remember that the absorption coefficient is a non-negative quantity, and so is the scattering coefficient, right? But when you do this construction, the scattering coefficient doesn't change sign, but the absorption coefficient will. Right? I'm doing this operation. It may not be positive. So there is still hope. If you're looking for only absorption coefficients which are non-negative, which is what we should be, maybe there is hope, right?
So phi is varies from 1 very small, but it is small, that's inside.
But that is possible, right? So it depends, right? So, but we'll see. So that it doesn't guarantee. So it says that there might be some cases where, as he said, if this is small,
yes,
compared to right, so then it still might be stay positive, right? So that's so. So you probably are not expecting a most general result, right? So, but let's see, what do we do have? So, okay, so yeah, but before I say this, right? So this is an example, construction of an example where there is non-uniqueness. Question is, are there other non-uniquenesses, or is this the only type of non-uniqueness you can have? Remember, we had the same question for the anisotropic, the elliptic problem, and that's one of the famous open problems actually. We had a way of constructing conductivity, two different conductivities which gave the same Griffith-Wyman map, right? And the question was, is that the only obstruction, the change of variable thing, right? And that is an open question. Here it is not an open question. So in a different paper, Stefan and Thompson proved for d greater than or equal to 3 that this is the only obstruction to uniqueness. Okay, so the converse part is hard. The easy part is to construct an example. Well, not easy, they were the first ones to do it. But proving the converse also takes some effort. Okay? So they showed this, that is the only obstruction to uniqueness. Okay? So knowing that actually helps you prove some theorems. And this is the corollary. So it says in d greater than or equal to 3, suppose you have two conductivities and two scatterings, which are positive, and your absorption is symmetric as far as the velocity direction is concerned, both of them, right? And your scattering coefficient is symmetric as far as the velocity direction is concerned. Then if the stationary albedo operators are the same, then sigma 1 equals sigma 2, k1 equals k2, even though they depend on velocity, right? And this is a corollary of this, because they know all the possible non-uniquenesses and the positivity and the symmetry actually help you with the. So, all right. So far I've shown you everything, like all the things which are true. What about things which are not, which are open questions? So there are people who do this, seriously, not just. So the thing is, what you want is you want to prescribe concentrations in every possible direction, right, incoming direction, and you want to do measurements in every possible outgoing direction. In practice, this, I believe, that's what I read in the review paper, in practice it's very hard and very expensive. Right? Imagine you want to know how many particles are coming out with this particular velocity at this point. So you have to have some way of absorbing only particles coming in that particular direction and no other. And then you do it at the same point for all this. So imagine how much time it would take to do this. I believe it takes time. So probably a more practical question would be, suppose your sources, you're not allowed to make up arbitrary sources depending on arbitrary directions, but there was some sort of restriction. And you couldn't measure in all outgoing directions, you could only do some sort of an average over the directions. Okay, so that's a lot less information. You don't have information for every possible direction. You're not allowed to put input in every possible direction. Then what can you recover? So here is one formulation. There are other formulations if you read the survey paper. So what you do is you do angularly averaged operator. So what you do is this. You take the same equation. This is the steady state equation. But now you prescribe concentrations on the boundary, on the incoming part. Well, right, on the incoming part, but the concentrations do not depend on the direction. Let's say you do that. There are other ways you can multiply it by a known function of position and velocity also. You can do that. All right, but let's just keep this very simple there. Okay, so this is all. You're not allowed to put a velocity there. And then when you measure, you don't measure u, x, v in all directions. What you do is you do some sort of average. At each point, you do an average of all the points. You basically compute the total flux, how many particles are leaving at a particular point. So this is sort of the outgoing, velocity times that, and you integrate it over all the possible directions at that point. So this is the total flux at the point x. So this is probably a more practical measure. Okay? So you're only allowed to put sources which don't depend on velocity. And you're only allowed to measure the total flux at a point rather than what's happening in each direction. And you're still trying to recover the absorption coefficient and the scattering. So well, let's do the parameter count, right? So your kernel depends on, well, you're allowed to vary x on the boundary, and what you're measuring is x on the boundary. So that's d minus 1, d minus 1, that's 2d minus 2.
For the directions, this you have 9 for it like a tensor, right? It's like a tensor, right?
What is like a tensor?
The outgoing direction will be a tensor. The incoming, that will be a matrix.
It's a vector.
Yeah, right. So the incoming will be another 3 by 3 matrix. So
no, incoming is a vector.
So totally, I'm saying if it's an
okay.
So totally 81 parameters or 9?
No. Let's talk about this later. So let's do a count. So there are 2d minus 2, beta depends on 2d minus 2 variables, and the absorption coefficient depends on 2d minus 1 and that 3d minus 2. In a bad situation. There's no way you're going to recover the velocity dependence, right? So what do? You try to say, well, let's assume that my velocity, so the absorption coefficient, the scattering coefficient, the velocity dependence is known in some way. Okay? And then just try to determine the dependence on the position. So this is what you might think, right? So let's assume the absorption coefficient depends on, it's some function of x which is unknown times a known function of position and velocity. There is velocity dependence, but it's known. Similarly, the scattering, it's a known function of position and incoming and outgoing directions times an unknown function of position. Okay? Now you do the albedo operator. So what is the unknown? So this is d and d, that's d, and your albedo operator depends on 2d minus 2. So that means for d greater than or equal to 2, you have at least the same right amount of information, and d greater than or equal to 3 is still an overdetermined function. And the question is, what do you know? And no one has answered that. The survey paper has some partial results on this, but this whole problem has not been solved. I'm just talking of uniqueness, not even reconstruction. Right? So this is one open problem in this transport. And so I will stop with the transport part here, right here. Right? So everything that I'm saying here, whatever I've said, it's in the survey paper or in the paper by Stefanov and just by Stefanov or the paper by Thomas. Those 3 papers, everything that I've said is there. Okay, so I'll talk to you afterwards if you don't mind, please, correct? So what I'm going to do is I'm going to switch gears now and talk of a hyperbolic problem. Okay? As you can see, the mathematics required for each type of problem is different. You're doing elliptic problem, there is no transport, there is no motion, and you have to do something different. Transport problems, there is, even in the steady state case, there is a little bit of transportation, there is movement there, like you think like that. Hyperbolic problem, there is always time dependence, there is motion, there are sharp fronts. Hyperbolic inverse problems, at least according to me, are very well behaved. Okay? If the hyperbolic regime physics suits whatever you're trying to do, meaning if you're trying to recover some things, and say the sound speeds of 2 different things is very different, which means this physics is good for you, then I'd say hyperbolic problems are a good way of doing it. But as you will see, hyperbolic problems and inversion is very well behaved. Many people say, no, inverse problems are always ill-posed, right? If you have the right amount of information, or it's an over-determined problem for hyperbolic, it's very complicated. Whatever few results are out there. Slava is, of course, another expert in hyperbolic problems. Do you agree with me, or?
Well, geometry.
Well, the geometry is good.
Right. Simple man. Otherwise, shape area.
Okay. So what I'm going to do is I'm going to show you, today I'll show you one example of just a one-dimensional problem, but it was a very important one-dimensional problem and non-trivial, as you can see, because of the people, because names are associated with that problem, as you can see. So whatever I'm talking about, actually, I've written some notes on this for myself, just to understand. And whatever I'm talking about, this was all done by 1981. I mean, in some sense, it was already solved by the 1970s. But whatever I'm showing you is, there were some parts which were done in 1981, 82. So all this is old stuff, well understood, at least theoretically. Numerically also it's very difficult stuff. Anyway, so I have notes on that, nothing very. Then all this was also done, explained very well in Browning's PhD thesis, which was written in 1999. He did some other things. There were some loose ends left, important loose ends that he handled. I hope you can get this on the web. Okay. And then there was a survey paper written by Bob Burridge in 1980, but it's not as complete as I would like it. Like there are parts of the analysis which are missing from there. So, but still, it's a good paper. Survey paper. Okay, so these are the three papers. By the way, I've already put my slides on the web. If you go to my web page, I didn't forgot to give it to me. But I'll make a few changes every time. Maybe after every day, if I find some errors, I'll fix it. So,
Okay.
Sorry.
This is recorded since this time.
This is right. Okay. All right. So what's the problem? Okay. I'm the least practical person there is. Okay. I know almost nothing about applications, but I'm interested, and it's very good to motivate things. So when I'm thinking, I make up, or at least I imagine some applications. I never get to the application, but it's right. So actually, this problem, the one I'm going to talk about is called is determining the shape of the vocal tract, and I was reading about it just yesterday about it. Like, who was the first person to do this? I think there's some guy called Schroeder or something, 61. But I heard of it through two names of two Indian electrical engineers, Gopinath and Soni. I don't know if you've heard of them, but so there were two electrical engineers at Bell Labs, which was AT&T. So I think some of them, one of them is actually probably even a fellow of the IEEE or something, if not both of them. So their problem was this, that, here is the vocal tract of a person, and they want to determine the area of the cross-section and each length along this. Okay, now why are we doing this, right? Okay, I'm imagining this. I'm not 100% sure this was the reason, but I'm guessing this. So they were working at Bell Lab, sound, speed, right? Telephones, right? So sound and stuff. So I think what they had in mind was that if you have someone who is deaf and you want to teach that person to speak, for us, when we're learning to speak, a very big part of this is our reinforcement from the ear, right? You say something, it sounds strange, you hear it, you correct it. So you're doing this as a child. That's how you learn to speak. And in fact, if you hear people who are deaf and when they speak, it's not that there's something wrong with their vocal cords. It's not they don't know how to correct what they're saying. Correct? That's the issue, right? They don't have this correcting, the reinforcement thing. So Gopinath and Soni were saying that, okay, so how do you do reinforcement? Nowadays, of course, they will maybe have a microphone and wire it to their brain, right? Now people are doing stuff like that, but I'm talking about 60s and 70s. Neurosciences were not as well advanced then. So what they said was, well, one reinforcement could be that you teach these people who are deaf to, say, make certain sounds on whatever. And then how do they know whether it's right or wrong? Well, they could be shown that, here's a healthy person with healthy hearing, and when this person makes a na or a sound, this is the shape of the vocal tract. So if they could determine the shape of the vocal tract of the person who is deaf, and when he's trying to make that sound, they could put side by side and say, oh, this is what you're doing. And see if you can have muscular control, and then you can adjust it. So what you need to do is you need to track the vocal shape of the vocal cord as the sound is being made. Correct? So I presume, I'm guessing now, I haven't read this anywhere, but I'm guessing this is what the motivation was. That they were trying to continually track the shape of the vocal cord of a person so that they could say to the person, okay, this is what it is. Right? I don't know if it's just a big story I made up or if it's really the truth. Okay. So you're trying to determine the shape of the vocal tract. So the vocal tract, of course, looks very rough, but I'm going to assume that it's like a tube with varying thickness, and all that is varying is the area of the cross section. And I'm going to measure a variable x, which is going to be along the length of the vocal cord. So x equal to 0 is here, and it'll go along that. So how are you going to determine the shape of the vocal cord? So what you're going to do is, you're going to set off a little, sharp sound or a sharp pulse of wave there. The wave will go and interact, and as, getting larger and bigger, it'll interact and there'll be something coming back. And based on as you measure that what's coming, the pressure wave coming back as a function of time. And based on the pressure wave as a function of time, just at the mouthpiece, you want to know the shape of this inside. Right? So that's a problem with the vocal cord. Of course, it ties in very well. What results for this is actually a problem which has been studied already from the 1950s. Okay? Which is, when you're trying to do things for, determining whether there is oil there somewhere or not, and you assume that the earth is layered, right? So remember what I'm going to do here. There's going to be a pressure wave. So there'll be at every point x and at time t, a pressure, acoustic pressure, and it'll interact with the area of the cross-section at that point, which is changing. It's a function of x. And you have set up some sort of an explosion or a very sharp, it's like what I mean is a delta function at the mouth, just at the mouth, not in the interior. It's like providing boundary conditions. So here is the area of the cross-section I'm going to call eta x. Okay? I'm not going to work with eta so much, I'll work with some function. U of xt is the acoustic pressure at x. X is measured from there at time t. And I'm going to not work with eta, but rather with a variable related to it called sigma, which is eta prime over eta. You can forget about eta. Eta is the area of the cross-section. Once you know sigma, and you know the area of the cross-section in the beginning, just by integration you get eta. So if you get sigma, you get eta. All right? So what's the physics? What's the connection between the area of the cross-section and the air pressure? And that the physics is, it's the wave equation. Sorry, can you see it? Or I'm going to write it several times. Okay, yeah. So it's just a standard first order wave equation, except now the coefficient shows up here. The unknown coefficient. What you're trying to recover, times use of x equals 0. So the physics now here is wave-like, the hyperbolic physics. Okay, so what's the setup of the problem? Remember, this is the connection. There is no pressure in the vocal cord before you start your experiment. So the initial condition is u of xt is 0 for t less than 0, assuming your experiment starts at time t equals 0. And then what is the input? What is the source? You're providing an explosion near the mouth, which means that's a boundary condition at x equal to 0, which is a delta function. So that's what I'm saying here.
So the question here, in order to get your sigma, there must be some approximation that you're saying it's just a tube, or because you're reducing spatial thing into an area.
Correct. So it's an approximation.
Some approximations.
It's just a model. I don't know, whether this was really used anywhere. So you could do a 3D model of that, and that problem would be unsolvable. If you assume that you really want to determine the shape, that's a 3D problem.
Yeah, 2D into 1, like many slices.
Well, right, but it's shaped in 3D. So you're trying to determine a surface. Of course, you're correct, but it's a shape in 3D. So.
Sure.
So here is the forward problem. This is the equation which is satisfied along the length of the vocal cord for all time. Your boundary condition, right? Hyperbolic problems need an two initial conditions or something for less than 0, one boundary condition. That's your source, the delta, the explosion on the other mouth. And then u is 0 for t less than 0. Everything is happening on the half plane for all time. And the question is, this is what you measure. So where does the measurement? Measurement is back at the mouth. So I don't know the physics very well. This is what you prescribe, and this is what you measure. Both at the same left hand at the mouth. And the goal is to determine the sigma x. Right? And once you know sigma x, you get eta x. You do the parameter count. The data depends only on type, one variable. Eta x or sigma x, whichever one you like, depends only on one variable. So it's a formally determined problem. Right? No extra data. That's the right amount of data. Okay. Okay, I forgot to say this. I didn't there. Right. So, what is the connection between this and this? Like, is it a linear problem or a non-linear problem? Right? The dependence of u on sigma is actually non-linear because of this multiplication. As you've seen in many problems, you know, if u1 corresponds to sigma 1, u2 corresponds to sigma 2, then u1 plus u2 is not the solution to sigma 1 plus sigma 2. Okay, just because it's multiplied. So because of that, you can see that the map from sigma to u0t is a non-linear map, and you're trying to invert non-linear. Okay? Inverting any non-linear map, hard, right? And we are talking of function spaces, I've said, rather than maps from R2 to R2 or R3 to R2. Okay. So, you know, this is a very good way of describing it. Distributions are great for thinking mathematically. But when you really have to work with it, you want to work with smooth functions, or functions at least which don't have chunks and stuff. But in this case, it's very easy to extract the singular and the non-singular part. So basically what happens is, I was running out of time, and I want to put slides on pictures on one page, but I can't. So here is the situation. Right, everything is happening here. And you prescribe your explosion right here. Right? Now, speed of propagation, this principal part is just the standard wave operator. Speed of propagation is 1. So things will move like this. So you have non-zero stuff here, and it will all be 0 here. Okay? So your capital U of xt is basically some function here, and it's something which is 0 here. And there is a jump. And the jump in the U is basically what gives you the delta. Okay? So what happens is you can replace this distributional problem. This is a very standard technique called progressing wave expansion. You basically try to write down the solution of this, and the most singular term is, basically you can write it down like this, and this quantity here gets replaced by, this tells you actually what is happening here. Okay? And you will see that in the next. So it's a very simple quantity. There's a way to write down the singular part. There's a way to write it down like this and describe what happens to you. So I'm going to write, instead of capital U, there'll be this function u of xt, which is only defined in this region. So all my analysis is going to be in this region. Okay, that's where my analysis is going to be. I'm not going to worry about it at all because it's not going to play a role. It's all 0 here. There's a jump. Okay. And so this problem is replaced by. So the U satisfies the same equation. It satisfies the same equation in this region. Okay? And then what about the boundary condition here? Well, ux0t was delta t. But, you know, so now I'm going to do it only on this. So all you left with is ux is 0 here. The delta t part has been accounted for by this jump here, which is given by this. It's a very standard calculation. You can show that the two problems are equivalent. That if you solve for capital U, you want to solve for capital U, solve the little u problem in this triangular region, and define the capital U to be u here and 0 there, then that function is the solution of the original problem. You think that's very standard calculation for hyperbolic things. Okay? This is the picture here. Okay. I wrote it as u equals 1 over eta, and this at least because if you go with the connection between eta and sigma, that's what it turns out to be. I didn't know how to put mathematical symbols here, so that's why. Okay, so the new problem is it's only occurring in this region here, okay, this big region here. Ux is 0 there, and you prescribe u on this in terms of sigma. So the forward problem is you give me sigma. You give me sigma, I can solve it. This is a non-traditional actually, but it's a well-posed problem. This is called a characteristic boundary value problem. Just the way you deal with initial boundary value problem, you can sort of tackle this the same way. And this is a well-posed problem. So if you give me sigma, I can define a map, and you can do the right spaces and everything. You take any sigma in L2 0x, and you look at, instead of U0T, I look at UT0T. That's the right space for it. And so what you do is, this is what your measurement was. Remember, you're measuring at what's happening at the end of the map, right? You're measuring U. If you know U0T, you can differentiate and get UT0. So if you knew sigma, you don't have to measure what's happening near the mouth. You can actually do it on a computer if you knew the thing. The inverse problem is, I'm telling you what's the measurement in the mouth. Can you tell me what the area of cross-section is? Right? So F is the forward, F is the map which takes coefficients, the area of the cross-section, gives you the measurement. I'm giving you the measurement. Can you tell me what the area of the cross-section is? And as I said, this is a nonlinear map on Hilbert spaces, and you try to invert them. Okay. So question is, how do you do this? So what are the questions? So if you have a nonlinear map, first question is it injective? Meaning, can two different areas of cross sections give rise to the same response? If that is so, too bad, you can't do it. Right? But that's first question. And if you're looking at nonlinear maps, you get some measurements, right? You make errors and stuff. So question is, whatever measurements, are they actually in the range, or are you off? So what is the range of this nonlinear map? Another difficult question. And if F is injective, then of course it has an inverse on the range. How do you construct the inverse of the range? And secondly, if you can't construct the inverse, is it stable? Meaning, if you make small errors, did you make only small errors here? Okay. So 4 questions. You have this nonlinear map. Remember how it's constructed. You take the sigma. Okay. US, you solve a problem in this triangular, in this upper triangular region. US is 0 and U is in terms of sigma. Okay. Given sigma, you can solve this problem, forward problem. You're trying to invert this map. Is F 1 to 1? Okay. What is the range of this map? How do you reconstruct sigma from this? And is this stable at all? And this is the only problem I know for which, well, nonlinear problem, for which the answer to all these questions. Okay? And it's a really serious, non-trivial problem. Okay. Imagine a nonlinear map from some Hilbert space to Hilbert space. We could answer all these questions. Right? So, and as you will see, the people who worked on it, you will not even imagine they were working on such things. So, but they did and solved this problem. And it's okay. So as I said, it's as complete an answer as I know for any nonlinear map. So who are the famous people? Carleman, right? I mean, representation theory and all kinds of things, harmonic analysis as well. He solved this problem. I mean, he made one of the major, Carleman, Levitan, famous crime, same functional car. Okay, well, I put his name. He's not in the same level, but he was my advisor. So the thing I'm going to describe is actually sort of a summary of mixture of whatever they did, and I'm more or less following the way science sort of looks at it. There are different ways to do it. Carleman and Levitan used some sort of integral equation method. Science had a slightly different approach. Science and crime had sort of like a similar kind of approach. Carleman and Levitan had an integral equation approach. So what are the results? Okay. So let me tell you the results. So firstly, F is injective. I'll characterize the range of F for you, meaning of course they did it. And a provable reconstruction, I'll give you a reconstruction algorithm and you will be certain that it converges to the actual answer. Okay. And stability, that's the stability you have. So of course this is an L2 norm, not an L infinity, right, which is really the more practical norm. So it says that if the response is closed in L2 norm, like accurate to say 10 digits, then assuming the constant, then the L2 norm of the 2 sigmas is also accurate 10 digits. No logarithmic stability or anything, that's Lipschitz stability. Right? Of course, it's not square or anything, that would be expected too much. But this is as stable a thing as you can expect, at least in the L2 norm. Right? Okay. So let me tell you about the characterization of the range. More than that also, the range is an open set. So, you suppose there is some actual measurement and you make a small error. So when you make an error, because the range is an open set, you're still not out of the range. As long as your error is not too much. Okay, so you will recover something and then the stability theorem will apply. Okay, so that's also another good thing. Okay, the range is an open set. And because the range characterization from that itself, you'll see why the range is an open set. Okay, so what is the range characterization? By the way, some of the names I haven't put, okay? So Lange-Wiesenski, of course, right? So there is the boundary control method which Slav was saying. So Lange-Wiesenski introduced that method for solving these problems, right? And the boundary control method is, as you can see, very powerful for certain types of problems, which I will talk about. Slav and I disagree on that a little bit, but it's a very powerful method, okay? And it can do things which I cannot do for certain problems. For example, for things where the velocity of the wave is not constant, those kind of problems, boundary control method is excellent. Whereas the methods I know are not so good for it. So,
but your methods have those properties of boundary control doesn't.
Right, correct. So it's maybe you should know both. That's right. All right. So, what about the range? Okay. So the range is okay. I just want to say one more thing. The picture. Okay. So of course, question is how long will you measure? No one measures infinite time, right? So let's say you measured for 20 seconds. Okay, 20 units. I'm assuming the length and the time unit are the same, right? I mean, you can normalize and everything. 20 units. So how deep can you go into the vocal tract? Signals travel with speed 1, right, in this equation. So get any information in 20 seconds, the deepest you can go is 10 seconds, 10 units. That's how as far as you can go. If you expect information from anything deeper in just 20 seconds, not possible, right? So the kind of thing you're expecting to do is, I'll give you the measurement of up to 2x, and all you can expect to do is recover the coefficient of interval x. Capital X is the capital X is there. And that's what we're going to do. So I'm going to always work with 0 to 2x, that's how far you measure, and then you will recover your function on the interval 0 to x. So suppose I give you some measurement, any function on 0 to 2x, right? And you say, can this be the response for some shape of vocal tract? Maybe every function in L2 0 to x is the response for some vocal tract. Maybe. Then the range is all of L2 0 to x. But the answer is it's not so. Okay? So what kind of functions which on the vertical line 0 to x could be the response for some vocal tract? And this was a characterization provided by the Gelfand and Charles. They said, well, take that function, whatever function it is, you want to test whether it's the response or not. And I create an operator on L2 0 to x, L2 0 to x. And this is the operator. Apply it to any function phi in L2 0 to x, and just take that plus this kernel. The kernel is formed by the response, right? The R that you're trying to test, that comes as the kernel. You define this operator HR, very nice operator, actually, right? And the answer is that you look at HR plus its adjoint. If it's positive definite, then R is in the range, meaning it corresponds to some vocal tract. If it is not positive definite, it doesn't correspond to any vocal tract. So that's a complete characterization of the range of this non-linear map. So, we have 5 minutes more. Okay, so how's the reconstruction? But I don't know if I'll finish it, let me try. So, how do we do reconstruction? Someone has given you that, my measurement, I went and measured this person's response, and I got this function R. No, of course you get it discrete, but this is all mathematics in theory. So you get this function 0 to 2x, and I want to know the shape of the vocal tract. Okay? So what is the sigma that I'm going to work with? I don't know what it is, right? So I say, pick any sigma. I don't know which one it is. Just pick any function sigma, and try this experiment. Try to do this. Oh, I should have put a pause. So let's just look at this part here for the first. Okay. You take that sigma and you solve this so-called sideways problem. So in the original problem, what you had was Vx was 0 on this, and you had V, the value of V here in terms of sigma. That is if you knew sigma. Correct? In the original problem. Vx was 0 here, and so ux was 0 here, and u was prescribed in terms of sigma. Okay, this is going to be important for us later. So notice that the value of u on this is related to sigma. Meaning if you give me sigma, I can get uxx. Conversely, you give me uxx, I can get sigma. Right? By just differentiation and so on like that. So it goes both ways, right? So I'm going to do the new problem. I'm going to just forget about this because I don't know sigma. I'm going to take ux equal to 0, but I have one more piece of information. I have the response here. I have u0t. So I'm going to throw this away, and I'm going to look at a new problem. This is 0, and u0t is the response I measured. And I'm going to solve a problem sideways. Okay, so let's look at this. This is what I'm doing. So I took it. That was my response. I don't know what is the right sigma. I said pick any sigma, it doesn't matter. Go ahead and solve this. So that's why I'm calling it V, I'm not calling it U, because it's some solution for some sigma. But what is the value of Vx on this? It's 0. What is the value of V on this? Well, you know Vt is R, so what is V? It should be +1. Therefore, what is a +1 here. So if you give me the measurement, then from that I can prescribe V0t and Vx here. Okay? It's a wave equation. Is this problem well posed? Is the answer to this true? And this is where the fact that this is a one-dimensional problem plays a very important role. One is used to prescribing V and Vt for the wave equation and solving it forward. But in one dimension, the role of x and t is reversible. You can think of this as time and that is space. You cannot do that in higher dimensions. This is very crucial. So you can solve the sideways problem. You provide V and Vx here, and you solve the sideways Cauchy problem. This is well posed. You gave me R, that was the measurement. You solve it. In particular, you can solve it over this triangular region. That's in fact where you can solve exactly. Right? Now remember, if it was the correct sigma, then Vxx would be actually equal to that. If it was the correct sigma. But I don't know if it is the correct sigma or not, right? If it was the correct sigma, sigma would be equal to this. So it's telling me what I'm looking for is pick any sigma, solve this problem, get this candidate for the sigma, and see if the two are equal or not. So you're looking for a fixed point. Right? So I'm going to reset this out. So what you're trying to do, I've reduced it to a fixed point problem. Okay? So given any measurement, I'm going to define a map from L to X to L. These are the spaces of the sigmas. You pick any sigma, okay? And you solve this V problem, the sideways V problem. Any sigma you solve, right? You prescribe V and Vx on the side, solve the V problem. Okay? And then for this V problem, this is the candidate for sigma. If it was the correct sigma, this would have to equal the same sigma. So I'm looking for a map from M sigma, which is this, and I'm trying to say, does it have a fixed point or not? If it has a fixed point, that's your answer. Right? Okay, so it's easy to, you can reduce many problems to fixed point problems. Question is, how do you prove it has a fixed point? Let's see that. Yeah. Well, find the fixed point. Right? Right. So what I can show you is this. That we do this problem, and if this x is small enough, right? Remember, this is going 0 to 2x and 0 to x. I give you up to 20 seconds. You don't have to use 20 seconds. You can only use 2 seconds. So first thing is that if x is small enough, you can prove this is a contraction. Okay, so all right, everyone can do that for small things. You can prove it's a contraction, so it has a fixed point. Then the second part is this. Okay, so I've recovered my sigma on this piece here, let's say. This was my full data. I've got it up to this much. But once I have my sigma, I can solve this problem sideways forward. I will get my new V and Vx here. And I will do the same contraction mapping argument again. Okay? And I'll get, again for small x, I can move forward. So you say, well, small x, you know, there's no reason to believe you'll reach the end. Unless there is a lower bound on the step size. And where does the lower bound come from? The positivity which comes from the range. That guarantees that there is a lower bound on the step size. So there is an estimate on the step size in terms of the operator MR, the HR operator. That's where positivity is used. Okay? If you can take a general R and do this problem and probably get some sigma, but you're not going to go very far. The positivity of that operator HR guarantees that there is a lower bound on the step size. Okay? And that is what makes the whole thing true. So all this, and this argument here, so finding a fixed point and a contraction mapping, it's a constructible thing. Right? So this guarantees it has a fixed point. So that's really the. So there is a continuation part and there is a guaranteed lower bound on the step size because of the range condition. And that's the one dimension. All right, thank you. And tomorrow what I'll do is, so I've shown you a one-dimensional problem which is solved. There are unsolved problems here, and there is. Even in 1D, there are unsolved problems. All right, thank you. Thanks very much.